examine the behavior of capacitors. So let's first examine the relationship between the charge Q and the voltage that is being applied to the capacitor. So let's say we have a capacitor. So the voltage across it is identified as V sub C. And let's say this capacitor is being connected directly to the voltage source V sub S. Now, if we do this, um, the capacitor will actually charge immediately with a Q equals to the relationship that we have covered earlier, which is C times the voltage applied to the capacitor. So since V sub C is equals to V sub S, so we have the Q there stored in the capacitor as C V sub S. Now let's say we charge the capacitor via a resistance. So let's say we have a series RC circuit, and the circuit is connected to a voltage source V sub S. Now when we do this, the capacitor will still charge, but this time on a gradual manner. In fact, it will be charging the capacitor in an exponential manner given by this relationship. Um, we'll derive this later if once we go to um, a more detailed examination of RC series circuits. Now let's call this equation 2. The rate of charging, so the capacitor is still being charged, but in, in an exponential manner, and the rate of charging is actually inversely proportional to the resistance that is in series with the capacitor. So meaning that the larger the resistance, the slower the charging of the capacitor will be. Now the rate of charging decreases as the voltage besides the voltage across the capacitor rises until it ceases when the voltage across the capacitor equals the charging voltage. So we can say that once charging stops, um, we say that the capacitor is actually fully charged. Now let's say we differentiate the equation 1. So equation 1 is this one. So let's differentiate both sides with respect to time, so we get this result. So this is a very important relationship that says that the current that is flowing towards the capacitor is actually proportional to the time rate of change of the voltage across the capacitor. Now if we apply this to the series RC circuit, we have an I that is a decaying function that starts at the maximum value V sub S over R, and then as time progresses, this current will actually decay towards a zero value. Now this equation number 3 tells us several things. First, that the current through the capacitor depends how fast the voltage is changing. So the higher the change of the voltage, the higher the current. Now when V sub Z is increasing, the current is actually directed towards the capacitor. That has a magnitude that is proportional to how fast that V sub C is changing or increasing in this case. When V sub C is decreasing, or that is we have a negative slope, that means the current is actually flowing away from the capacitor. And how fast is the current flowing again depends on the magnitude of dBc dt. Now, this equation 3 also shows us that the the voltage V sub C across the capacitor cannot change abruptly. So let's say it changes from a particular value and then changes immediately to zero. That cannot happen because that would mean that the slope will actually be very high. Ideally, it can be infinite. And that means uh, I must be very high as well, as shown by equation 3, or ideally infinite, which is impossible to happen. Now, for the current voltage relationship, uh, we can also solve for the voltage across given a current function. Um, and if we simplify this, so the voltage is actually equals to the integral of I dt plus an initial value of the capacitor. So initial voltage of the capacitor. Simplifying this shows us that the voltage across the capacitor is really the voltage due to the change in the accumulated charge plus any initial voltage. For the power and energy, um, the power absorbed or released by the capacitor uh, st still follows the equation for power. So we simply multiply the voltage and the current. But since current is C dV C dt, we can use this and plug this into the equation for power. The energy absorbed or released by the capacitor can be derived by simply integrating the formula for P dt. So since P is given by this one, we can use this and plug it here, and you will get 1 half CVC squared. And since we have a relationship Q equals CVC, we can also express the energy absorbed or released by the capacitor in terms of the Q that is being stored by the capacitor.
A capacitor can either be in a transient state or in a steady state. A capacitor that is in a transient state means that the voltage across it and the current through it are changing over time, while a capacitor that is in steady state, the voltage and currents are all constants, or it could be zero. What is interesting about a capacitor that is in steady state is that its current is a zero because the voltage is a constant. So if the voltage is constant and I get the derivative of that voltage, that will give me a zero, that will make the current zero. Now, if a current is zero through the element, means that that element is like an open circuit. So if this is a zero, this element is like an open element or an open circuit. Let's say we have a circuit that contains a capacitor, and that capacitor is undergoing a transient condition. So that circuit is said to be also undergoing a transient phase. Okay, that means the voltages and the currents in every parts of that circuit are all changing. While a circuit that contains a capacitor that is in steady state, that circuit is also to be the circuit is said to be in steady state condition as well. Now, a circuit that is under steady state is sometimes said to be under DC conditions. A circuit in steady state can transition to a transient state if it is or if external forces is applied on that circuit. So for example, if we change the voltage of a voltage source or the resistance of one resistor, that will trigger a transient uh, condition. However, that circuit will eventually go or settle to a new steady state if there are no further external um, factors applied to that circuit.